Title: Hi, I'm DG. I built a machine learning model to predict the energy output of a combined cycle power plant, using 9,568 hourly sensor readings with Python and scikit-learn. Problem definition: this is a supervised learning regression problem. We are predicting a continuous numerical value, the net energy output in megawatts. I chose R² as the primary evaluation metric, which measures how much better our model is compared to simply predicting the mean. I also tracked RMSE and made to give error in interpretable units. Features and correlations: the dataset has 4 input features. Temperature and exhaust vacuum show very strong negative correlations with energy output. As temperature goes up, power output goes down, which makes sense from a thermodynamic perspective. Ambient pressure and relative humidity have weaker but still useful positive correlations. I used all 4 features since there's no dimensionality concern with only 4 inputs. Data splitting and validation: I split the data 80/20 into training and test sets. The test set is completely held out and only used once at the end. This prevents data leakage. For model comparison, I used 5-fold cross-validation on the training set, which is more robust than a single validation split because every sample gets validated exactly once. Algorithms considered: I compared 4 algorithms across 5 configurations. On the parametric side, linear regression is a simple interpretable baseline, and ridge regression to handle potential multicollinearity. On the non-parametric side, random forest, which uses bagging to reduce variance, and gradient boosting, which builds trees sequentially to correct errors. I also tested 2 random forest configurations with different tree depths to compare hyperparameter effects. Cross-validation results: here are the cross-validation results. The 2 linear models performed identically at R² 0.928. Ridge added no observable benefit on this dataset. Random forest improved significantly, and gradient boosting came out on top with R² 0.961. The lowest RMSE of 3.37, and the lowest MAE of 2.44. It also had the most consistent results across folds with the smallest standard deviation. Final model. Test set evaluation: I selected gradient boosting as my final model and evaluated it on the held-out test set. R² came in at 0.9655, meaning the model explains 96.6% of the variance in energy output. RMSE is 3.16 megawatts and MAE is 2.33 megawatts. That's roughly 0.5% average error relative to the mean output. Compared to the linear regression baseline, that's a 30% reduction in prediction error. The actual versus predicted plots on the right show how much tighter the gradient boosting predictions cluster around the diagonal. Model demo. Code and output: here's a quick look at the actual code and output. On the left you can see the key section of the Python script. I used scikit-learn's gradient boosting regressor with 200 trees and max depth of 5. On the right is the terminal output showing the full model comparison summary table and the final test set metrics. The complete source code is roughly 200 lines in a single self-contained file called model.py. Feature importance: looking at feature importance from the gradient boosting model, temperature dominates at about 55%, followed by exhaust vacuum at 25%. Humidity and pressure contribute smaller but meaningful amounts. This ranking aligns with thermodynamic principles. Temperature directly determines the Carnot efficiency limit of heat engines, so it makes sense that it's the strongest predictor of power output. Key takeaways: 4 key takeaways. First, nonlinear ensemble models outperform linear ones by capturing feature interactions. Second, temperature alone drives over half the prediction power. Third, the model achieves practical accuracy. 0.5% average error is viable for real-world energy forecasting. And fourth, proper validation methodology matters. 5-fold CV with a held-out test set ensures our results are trustworthy and generalizable. Thank you. That concludes my presentation. The project was built with Python, Pandas, scikit-learn, and Matplotlib, using the UCI combined cycle power plant dataset. Thank you.